After having understood the modal field patterns of a step index optical fiber, now let us have a look at what is the fractional power in the core, how the power is distributed between the core and the cladding. So, again we are analyzing this kind of step index optical fiber, and we know that the power is proportional to, if psi is the modal field which is basically the electric field, then the power is proportional to the electric field square integrated over the entire transverse cross section. So, if psi is the modal field, then the power would be proportional to integral over r phi mod psi square r dr d phi. So, in the core it would be given by some constant q, and this integration over r would be from 0 to a, and if I want to calculate the power in the cladding, then this integration over r will go from a to infinity, because I am considering a case where the cladding is infinitely extended. So, let us calculate the power for even modes. For even modes, the solutions psi r in the regions core and the cladding are given by this, where a and b are related to each other by boundary conditions. Here I have used the boundary condition that psi r is continuous at r is equal to a. So, a j l u is equal to b k l w, and let me equate to some other constant c. So, I can get these a and b in terms of a single constant c. So, p core is this, and if I now substitute the modal field of the core, then it would be of the form j l square u r over a r dr, and then phi part would be cosine square l phi d phi, and this would be the constant which comes out, c square times q, and then there would be j l square u. For a given mode, even j l square u would be constant, because beta is constant for a given mode. So, this I can simplify like this, phi solution, the phi integral is straightforward, and then it can be written in this particular form by doing some mathematical manipulations. If you are interested in the details of this, then you can refer to the book Optical Electronics by Ghatak and Tyagarajan, or to Introduction to Fiber Optics by Ghatak and Tyagarajan, any of these books. So, there are the details. Similarly, in the cladding I can get the power as this, where g is a constant. Then I can find out the fractional power as power in the core divided by total power, and I can express this in this particular form, and again the details can be seen in this book. So, I have the fractional power in the core given by this expression. Now, I am interested in how does this look like when I vary V, when I vary the parameters of the fiber, and in this way I vary the value of V, normalized frequency, then how the power in the core and the cladding is distributed, how this distribution changes. So, for that let me plot this eta fractional power as a function of V, and this has been taken from this paper. I have adopted this, so it is slightly modified. So, what I see that if I increase the value of V, then the fractional power in the core increases. This is a very simple observation here. Another thing that I see is that for LP01 mode and LP11 mode, LP12 mode, this starts from 0, while for these modes this starts from 0.5. And what I see that if I do a little mathematics, I can show that for L is equal to 0 mode, as the mode approaches to cutoff, then the fractional power can be given by eta tending to 0 for L is equal to 0 and eta tends to L minus 1 over L for L greater than or equal to 1. So, I can see for LP01 mode the cutoff is 0, LP01 mode the cutoff is 0 and L is equal to 0. So, as I approach to cutoff, the power is 0. And if I take LP11 mode, then again eta is 0. LP11 mode cutoff is 2.4048. So, as I approach to cutoff at 2.4048, it will start from 0. However, for L is equal to 2 mode, this would be half. So, L is equal to 2 mode, LP21 mode, the cutoff is around 3.8. So, around 3.8 it will start from 50%. Okay. So, this is how the power of different modes is distributed among between the core and the cladding. And I can see that as V increases, there is more and more power confined in the core, and therefore the fractional power in the core increases as V increases. This I know from the theory of planar waveguide also. Okay, we have seen that. Now let us see some examples. For a fiber with N1 is equal to 1.45, N2 is equal to 1.44 and A is equal to 4.5 micrometer. If I calculate the value of V, then it comes out to be 4.135 at lambda is equal to 1.55 micrometer. And then if I see the fractional power in the core for various supported modes, then it is given like this. For LP01 mode, 95% power is in the core. So, if I look at the mode intensity plots, then 95% power is in the core. This dashed line corresponds to the core cladding interface. So, most of the power is inside the core. For LP11 mode, about 86% power is in the core and 14% goes out. For LP21 mode, 68% power is in the core, and for LP02 mode only 38% power is in the core. So, I see that as I go towards higher order modes, the fractional power in the core decreases, because higher order modes are closer to cutoff. If I look at how the power at different wavelengths is distributed between the core and the cladding, so for that I consider a fiber with N1 is equal to 1.45, N2 is equal to 1.44 and A is equal to 4 micrometer, and then here I have tabulated the fractional power in the core for LP01, which is the fundamental mode, and LP11, which is the first higher order mode. Okay. So, I see that at 0.65 micrometer wavelength, more than 98% power for LP01 mode is located in the core and 96% power is located in the core for LP11 mode. So, as I increase the wavelength, I see the general trend that the power in the core for a given mode decreases. So, as I increase the wavelength, the mode spreads out, because I know if I increase the wavelength, which means I am decreasing the value of V and the mode approaches to cutoff, and when a mode approaches to cutoff, then the field spreads out. So, the fractional power in the core would decrease. If you look at the modal fields of LP11 mode at 0.65 micrometer wavelength, then it looks like this, where the value of V at this wavelength is 6.57. So, high value of V. So, so most of the power is in the core. But if you go to 1.7 micrometer wavelength, the value of V is 2.5, which is very close to cutoff. The cutoff is 2.4048, and then I see that the field spreads out, okay, and there is only 37% power in the core. What happens if I change the numerical aperture of the fiber? So, for that I take a fiber with cladding refractive index 1.444, core radius 4 micrometer, and I analyze it at 1.55 micrometer wavelength. So, now I change the value of numerical aperture. Then what I see, as I increase the value of numerical aperture, then the fractional power in the core increases, and this is intuitively correct. I expect this intuitively, that as the index difference between the core and cladding increases, then more and more power is pushed inside the core. The index contrast between the core and the cladding increases. So, intuitively I think that the core cladding interface, this boundary is hard to penetrate for the field, and so less field extends in the cladding region, and there is more and more field in the core region. So, that is why the power in the core region increases. The fractional power in the core is very high if the value of numerical aperture is high. When the numerical aperture is low, very low, it is 0.05, just 0.05, it is very weakly guiding fiber. Okay. So, it hardly guides light, only 14% of light is in the core, and 86% light spreads out in the cladding. So, it has really very poor guidance. The value of V is very small, 0.87, quite close to 0, and when the numerical aperture is high, then of course the entire field is pushed in the core. The value of V is very large, about 5.7. Now, after this I would like to focus on single mode fiber, and because single mode fiber is the fiber which is used in long haul telecommunication system, and I would like to first look at some very important parameters of a single mode fiber. What are these parameters? One is cutoff wavelength. What is the cutoff wavelength of the fiber? What is the spot size or mode field diameter or effective area of the fiber? What is band loss? And what are the dispersion properties of this fiber? So, we would look into these in subsequent lectures as we go along. So, let us first look at cutoff wavelength. What do I mean by cutoff wavelength? If you look at a fiber, then the single mode condition is given by V is less than or equal to 2.4048, equal to sign corresponds to the limiting case, and V is given by 2 pi over lambda naught times A times square root of n1 square minus n2 square. So, if I find out the wavelength corresponding to this value of V 2.4048, okay, then this wavelength will come out to be 2 pi divided by 2.4048 times A times square root of n1 square minus n2 square, or I can also express it in terms of numerical aperture, because square root of n1 square minus n2 square is nothing but numerical aperture, or I can also represent it in terms of relative index difference delta, because delta is n1 square minus n2 square over 2 n1 square. So, in this way I can calculate the value of lambda c, and what happens that for all the wavelengths greater than lambda c, the fiber is single mode, and for wavelengths smaller than lambda c or shorter than lambda c, the fiber is multimode or few moded. This wavelength lambda c, give you a demarcation between the single mode operation and multimode operation. Although this wavelength corresponds to the cutoff of LP11 mode, but in general we call it the cutoff wavelength of the fiber. So, when I say cutoff wavelength of the fiber, then it means the cutoff wavelength of LP11 mode of the fiber. Next thing is propagation constant. If I look at the BV curve of LP01 mode, because it is a single mode fiber, so only LP01 mode is guided. If I look at the BV curve of LP01 mode, it looks like this. Okay. This I have obtained by solving the transcendental equation corresponding to L is equal to 0 mode and extracting the first root of that, which corresponds to LP01 mode. So, this exact means by numerically solving the transcendental equation or eigenvalue equation. So, it goes like this. So, do I need to refer back always to this curve? If I am given a fiber and wavelength, then I know the value of V and I want to find out the value of B or propagation constant, then I need to refer back to this curve always. Can I do something that I can fit some equation to this, so that I just use that equation and extract the value of B if I know the value of V? And it can be done. What is seen that if you fit this equation to this curve, then it fits very well for A is equal to this and B is equal to this in the range 1.5 to 2.5, in the range of V which goes from 1.5 to 2.5. So, this is an empirical relation between B and V, which is given by A minus B over V whole square, where A is equal to 1.1428 and B is close to 1. So, I can always use this empirical relation if the value of V lies in this range to obtain the propagation constant of LP01 mode of the fiber, and it becomes very handy while doing calculations. How good this approximation is, how good this empirical relation is, for that I have superposed the values of B obtained by this empirical relation on the values of V which I have obtained by solving the transcendental equation, and I find that the agreement is quite good. If I look at this graph, I can also have the quantitative estimate of this fitting, how good this fitting is. That I will do in the next slide. But if I know now, if I now know this empirical relation, then my life becomes very easy. I need not to go to solve the transcendental equation again and again. For example, if I have a fiber with N2 is equal to 1.45, delta is equal to 0.64%, A is equal to 3 micrometer, and I consider a wavelength of 1546 nanometer. So, these values correspond to a value of V which is 2, and if I put it here, then I find out the value of B immediately as 0.41616, and from there I can extract the value of N effective. Now, coming back to how accurate it is, I have tabulated the values of B obtained by solving the transcendental equation and obtained by the empirical relation given in the previous slide, and I have looked at the percentage difference between the two, and I see that the maximum difference is 0.23% in the range of V going from 1.5 to 2.4. So, in this range it is a very good approximation. I can use this empirical relation without any problem. Next important parameter of a single mode optical fiber is the spot size. When power exits from a single mode fiber, and if I capture the field or the intensity which comes out of the fiber just at the output end of the fiber as it exits from the fiber, then it looks like this. When I look at it, then it very much resembles to with the spot which comes out of a laser beam. So, it immediately tends me to think that whether can I approximate it by a Gaussian, because the output of a Gaussian is output of a laser is Gaussian, of a single mode laser. So, what I try to fit a Gaussian to this kind of distribution, and that Gaussian I represent as psi r is equal to a e to the power minus r square over w square, where a represents what is the value at the center and w is the width of the Gaussian. So, what I do, I plot the exact field in blue line which I obtain in the form of Bessel functions, and then I plot in green color the best fitted Gaussian. How do I fit? I will explain in the next slide. And what I see that this fitting is very good. This fitting comes out to be very good, at least for this case. So, I can very well use this Gaussian approximation to represent this field. And why I want to do this? Because using Bessel functions all the time is not a convenient thing, okay, and working with Gaussian is very easy. So, I express my modal field with a Gaussian, and then with the help of this I can estimate or define the spot size, the size of this spot. As you know that the field goes down to 0 when r tends to infinity, but what is the size, what is the region in which the maximum field is there? So that we can define by r is equal to w, because at r is equal to w the modal field drops down to 1 over e of its peak value and intensity drops down to 1 over e square of its peak value. So it can give me a good estimate of the size of the spot. So this w is known as Gaussian spot size, and 2w, twice of this value, is basically the diameter, mode field diameter, and I can find out the effective mode area by pi w square. How do I find out the best fitted Gaussian? The best fitted Gaussian has two parameters. So I need to optimize two parameters, A and W. A is easy to do because it can be found out what is the maximum value of the field, and to find out W, what I do, I take the overlap of this Gaussian with the exact field, which is defined in terms of Bessel function. So I take this overlap of the Gaussian with this field and I vary the value of W in order to obtain the maximum value of eta. The value of W which gives me the maximum value of overlap, that gives me the best fitted Gaussian. Okay, then I tend to think just in the same way I have defined an empirical relation between the propagation constant and V, can I do the same for the spot size also, so that I need not to all the time fit this Gaussian. So there is an empirical relation which relates the spot size with normalized frequency V, and it has been given by D Marcuse. So with this relation I can find out the spot size of a given fiber if I know the value of V, and this empirical relation is quite accurate in the range of V from 0.8 to 2.5. So if I plot it, so it goes like this, and this is an obvious result that as I increase the value of V, I know the confinement in the core increases, and therefore the value of W over A would decrease. Now let me find out how accurate this approximation is, how accurate this empirical relation is. So for that I take two representative points. One is for smaller values of V, that is at V is equal to 0.9, and if I see the modal field here, it looks like this, and I find out the value of W by two methods. One is by Bessel functions, the exact value, and another is from empirical relation. So I find that at V is equal to 0.9, the exact value of W is about 30.7 micrometer, while empirical relation gives me a value of 31.8. I take another representative point at V is equal to 1.8. At V is equal to 1.8, this is the modal field, and the value of W obtained from exact and empirical formula give me almost the same value, they are in good agreement. So I find that for lower values, for smaller values of V, there is some discrepancy, but this empirical formula works very well when I go towards higher values of V. Now, let me look at the fractional power in the core, okay, and see how good the Gaussian approximation and empirical fitting is. So, what I have done? Well, I have calculated now the fractional power in the core, which is given as P core over P total, while considering the Gaussian spot size. So, as I have said that it is very easy to work with Gaussians. So, now calculating these integrals would not be very difficult if you use psi as a Gaussian. So, when I do this, then it comes out to be 1 minus e to the power minus 2a square over w square, and when I plot it, it goes like this. Okay. To find out how accurate it is, I again take two representative points at v is equal to 0.9 and at v is equal to 1.8, and I find that at smaller values of v there is a huge discrepancy. It is because at lower value of v there is a small discrepancy between the exact value and the Gaussian and empirically fitted value, but this small discrepancy is amplified because this appears as it appears in the form of e to the power minus something. So, this gets amplified a lot. However, at the higher values of v, the discrepancy is small, and therefore the discrepancy in fractional power is also very small. So, the agreement is good. So, in the next lecture I would look into some other ways of defining the spot size, and I would also look into various examples to understand the cutoff and spot sizes. Thank you.